All right, let's start. So there's a few extra seats in the front. There's extra chairs and tables. If you need extra seats, they're up here. If anybody wants to add, there's still a few positions to add as long as there's seats in the room, I guess. People who have a need to take this class this semester in order to graduate on time will get priority, but we can add a few people. So this is theory of computation. Let's start with an interesting problem. You have a 12-hole centrifuge. The question is, can you put 5 test tubes in these 12 holes in some manner that will keep it balanced if it starts to spin? So there's no dirty tricks here. The holes are like the hours on the clock. All 12 equally spaced. And the test tubes, again, no tricks. They're all equal size, equal mass, equal density, equal weight, and so on. So that's the question. And so try to, in the next half hour, as we tell you about some other stuff that doesn't require full processing of your brain, try to figure out this problem. So again, the question is 12 holes, 5 test tubes simultaneously. You can't do 2 and then switch 2 with 1 more. You got to do all 5 at the same time. So there's no dirty tricks here. None of the questions I'll ever ask you in this course will be some sly trick or something to play gotcha with you. It's all honest to goodness logic, reasoning type questions, right? The kind of stuff that you'll see in Google interviews. So this kind of question can actually help you get jobs one day. Let's take a quick poll. How many say 5 are possible? 5 test tubes simultaneously are possible? Raise your hand. How many say impossible? 5 just don't have. Oh, it's a pretty equal split, you see. So that makes it even more interesting. If a class of clever students like yourselves kind of split on a yes/no question, that makes the question kind of interesting, right? Okay, so we'll come back to that later in this lecture. Meanwhile, here's our textbook, Theory of Computation. It's the 2nd edition, not the 3rd. The 3rd just costs more, and it doesn't much change from the 2nd edition, so I figured we'll stick with the 2nd edition. And on the website, there's actually a link to the PDF if you look hard enough. So my gift to you. Of course, respect copyright laws, and if you get use out of that, you may want to buy a used version on top of that, so you have a hard copy as well if you'd like. Another good book I'd like you to read is How to Solve It by Polya. It's an old book, but it's very, very still current in terms of what it teaches. And what it teaches is general problem solving. How to be an intellectual MacGyver when you're presented with a problem or a challenge. And very, very good book. It's short, just got maybe 100, 150 pages. It's paperback, but probably one of the best books you'll ever read in terms of value. This can help make or break a Google interview for you. So, it's when I say value, your salary is on the line potentially. If you read this book, you'll be much better off. If you want to brush up on algorithms, this is a good book. Introduction to Algorithms by Corman. How many have seen this book before? It's pretty popular. And the reason I know it's a good book because on the back cover they quote me as saying that it's a good book right there. So must be good. So I'm not gonna lie about that. Right? The cartoons you can sort of see offline. It's an encouragement to get you to look at the slides other than the lecture, and sometimes we'll present a few key cartoons that are particularly relevant. So here's kind of an outline of the course, what we want to accomplish in the next 3 months or so. First, we're going to go through some history of computing all the way to Aristotle. And it might seem strange to you why I'd want to start with the ancient Greeks when I talk about computer science, because it all started there. Mathematical systems, axiomatic systems, ways of proving things, inferring things, reasoning about things, logically, rationally, it all started with the ancient Greeks, pretty much. So we're going to show you the connections all the way from back then to the present time through a whole bunch of other individuals that made huge contributions to the stream of consciousness that now we call computer science, which permeates all the other fields, by the way, as you know. So we'll get to that. We'll try to breeze through it, a little bit faster than usual, so we don't take too many weeks on this. But as we talk about this history, it's not just history. We're going to actually prove theorems as we present the work of these people to you and explain to you what they did and why they did it and how they did it. We'll actually show you theorems and proofs, and it'll be very interesting. So a lot of knowledge will be embedded in this historical backdrop of discussion, which is how I like to present it, because then you'll see the whole thing end to end, how it all started and where we ended up today and why. How did we get from there to here? And how did we get from abacus to iPhones, and everywhere in between? Just fascinating, you'll see. And then we'll talk about fundamentals such as set theory, predicate logic. Some of that stuff I assume you heard in discrete math before, but we'll start from first principles anyway and explain everything at least once. And on the class website, there's some handouts that kind of go through some of the basic set theory and predicate logic, but we'll mention it here too, although briefly, just so there's really technically almost no prerequisites to this course other than your willingness to catch up if you're fuzzy on some concepts. And then we'll go to formal languages, the Chomsky hierarchy, a piece of which looks like this. The context-free languages, the regular languages, the citable languages, recognizable languages, P and NP when we talk about NP-completeness. And we'll spend several weeks on that, and we'll take it as it goes. Non-determinism, that's a very important concept that permeates P and NP relationships. And we'll talk about undecidability. It turns out that some problems cannot be computed. They can be stated. They're easily definable. They're very simple Boolean predicates even, yes, no functions that you can easily define. They certainly exist and easily defined, but there's no algorithm for them ever to compute them. Not because it's hard enough so that the algorithm will be very complicated and it's too long and we haven't discovered it yet. It simply doesn't exist. So it's not like looking for a prime number past the Googleplex, which we know exists because there's infinity of primes. It's like trying to find an integer between a quarter and a third. That doesn't exist. That's a very different story, no matter how hard you look. And we'll talk about models of computation, such as DNA computing and cellular automata and many others, and talk about their equivalent, i.e. the notion of universality in computation. There's many models of computation. We don't have to use silicon and transistors to compute. We could use proteins to compute. Can anybody give me an example of a pretty sophisticated, amazing, even protein computer that's made of proteins? Yeah, we are. Look in the mirror and you'll see one. And it's a pretty good one too, because these computers here, these iPads and iPhones and all these computers are output of this protein computer. It's not the other way around. This thing didn't invent us. We invented it. And even it is pretty sophisticated, so we must be more sophisticated than that even if we came up with that. Right? So there's many, many other models of computation. They're all equivalent. We'll talk about that too. When we get to NP-completeness towards the end of the course, or the last third of the course, we'll explore interesting relationships between time and space and non-determinism and determinism, like unbounded parallelism and serial kind of computations, and what you can do with either one and how they relate. Very interesting stuff. Very powerful theory. It can save you a lot of time and energy by telling you that certain problems are too hard to try to solve exactly in polynomial time. So either you can not bother trying to solve them in polynomial time and accept exponential time solutions, which is not too cool because they take too long, or you can resort to heuristics, rules of thumb, and then try to solve them approximately but not exactly, like traveling salesmen and bin packing and satisfiability and many other problems that are all NP-complete. So that's kind of an NP-complete section of the course. We'll go through that for a couple of weeks. And we'll introduce some advanced topics, generalized number systems, oracles, relativized computation, zero-knowledge proofs, very cool stuff. Zero-knowledge proof is how you can prove something to somebody without showing them the proof itself. You can convince them that something is true, and they'll be arbitrarily assured that you're right, but you never have to show them the proof at all, none of the proof, which is an amazing concept. It sounds almost impossible. It sounds that you can't possibly accomplish something like that. Prove to somebody something without actually showing them the actual proof. But you can do this, it turns out. And that's zero-knowledge proofs. And we'll look at the Turing test and talk about other advanced topics towards the end of the course, and artificial intelligence and robotics and so on. So generalized numbers, I just mentioned them, but just so you see it at least once, and maybe we'll get back to it later. We all know the reals, the rationals, the complex numbers like 7 plus 3i. The greens are examples. And this is a Venn diagram. It's a nested set containment diagram there. But there's things outside these. What's a generalization of complex numbers? Anybody heard of any? You have like vector fields, and you could talk about quaternions, which are I plus j plus k type numbers. And then octonions, sedentions outside that. Here the sedentions have 16 components. Right? The quaternions already are non-commutative. The octonions are non-associative. And then you have other types of numbers out there that are much more generalized than real numbers. You have some numbers that are called surreal numbers. I won't bother to tell you what it is right now. It's a bit complicated. But one of the papers on the class website that you can read for extra credit is all about surreal numbers. Very cool stuff. And then you have circumplex numbers. A plus bi, I is still the square root of minus 1. But A and B are no longer real. They're surreal. So this is not a joke. These are much more general numbers than you've seen so far in your life, perhaps. And if you haven't seen them yet, my gift to you. Right? I mean, you could have gone your whole life not knowing about complex numbers. It wouldn't be a bad life. It'll just be a little sad that there's all these complex numbers out there, and you could do all sorts of magical things with them that you can't do with reals, and that you've never heard about that. Right? I mean, you could have gone your whole life just thinking of there's only integers and not even fractions. In fact, the ancients were exactly in that predicament. And so if you don't know these advanced, more generalized systems out there, it's not terrible, it just hobbles you. It restricts you and basically prevents you from doing more abstract kind of thinking and reasoning and engineering and science. And without fractions, without real numbers, we wouldn't have iPhones. If all we had was integers, there's relatively little you can do with that. You can count stuff on your fingers and count up apples and oranges and still trade in markets and do bartering and that kind of thing with integers only. But you couldn't compute compound interest, right? So even financial things that are useful require real numbers, not just integers. Anyway, we'll prove certain things later on, so that some real numbers are not finitely describable even. There's no finite description to describe them. And so these numbers here in purple are in this region, right? They're real numbers, so they're in this purple oval, but they're not describable. So the finitely describable numbers are this boundary here in this Venn diagram, and these are right outside that boundary. And some finitely describable real numbers are not even computable. That is, you can describe them finitely, sure enough. Things like in red here, color-coded. But no algorithm can spit out the digits. Not even any digits, not just, never mind, the whole representation could be infinite. So some real numbers that are not finitely describable are not pi and e and square root of 2. Those are perfectly finitely describable. I just described all three in one word, in one breath, right? Pi, diameter of a circle, circumference of a circle ratio to its diameter, that's pi, that's a finite description. E, natural base log, you also describe it as a limit. Square root of 2, it's the real number that when multiplied by itself gives you 2. I just described it finitely. So those are all finitely describable numbers, but some numbers are not finitely describable no matter what. It's not that we're not smart enough to come up with a finite description. Finite description does not exist to be found by anybody, however omniscient or clever. That's a very strong statement I just made, and we'll prove that mathematically as we talk about the history of all that stuff. Speaking of Venn diagrams, here's another cool Venn diagram. This is the Chomsky hierarchy. So you got regular languages that are contained strictly within the context-free languages, which are contained within context-sensitive languages, and finally out here you have decidable languages, and so on and so on. So this Venn diagram here is sort of a cornerstone, a touchstone in this course. We'll come back to it again and again and keep describing certain regions of it and their relationships among each other. And so this is a very important diagram. And there's also some infinite hierarchies in between these. So it can get arbitrarily deep and convoluted. There's many, many regions to this. I'm just showing you, just a couple of dozen regions. But there's hundreds of regions that have names and an infinite number of regions that don't have names. It's just too many to name. But these are some of the named ones. It's so important that we assign names to them, like P and NP and exponential space and decidable and recognizable and not recognizable. So these are kind of the common bread and butter kind of pieces of this Venn diagram that we'll harp a lot about, but it's a lot more complicated than this. So this is sort of the diagram that we'll keep filling in like a jigsaw puzzle throughout the course. And by the end of the course, when I show this to you on the last day, you'll know a lot about each one of these regions and each one of these names and their properties and how they interact and how they interrelate to each other and how they're contained or not contained within each other and so on and so on. So basically, this is sort of the one slide that best captures most of what we'll learn in this course. Any questions, by the way? If you have any questions, stop me and I'll be happy to answer them. Don't want it to be a monologue. We'll get into interactive sessions pretty quickly. So the philosophies, I want to show you the big picture as much as possible, not just give you tidbits of information that are disconnected and expect you to memorize them like a parrot. That's not how I teach. That's not how people should learn. You should see the big picture. Always keep in mind how everything kind of fits together on the grand scale. The scientific method, very important. Occam's razor, simpler is better, whether it's in proof, in architecture, in art, in design, in engineering, less is more, right? You know, there's a reason why electric cars are much more reliable. They have much fewer parts. The most reliable part of any machine, the most reliable part of any device, the most reliable part of any program, the most reliable subroutine that exists in your code is the one that's not there. Think about that. That's an interesting mindset. It's a design principle, very powerful. Occam's razor, less is more. We'll come back to that too many times. So prerequisites, not a whole lot. A little bit of discrete math will be helpful. A little bit of algorithms will be helpful. I think most of you have had that here. If you're a little bit rusty, you can look stuff up. You can look at some of the handouts I put on the class website to brush you up on some discrete math and set theory and a little bit of algorithms and that kind of thing, which will come in handy. So there's not a whole lot of onerous requirements for this course other than a lot of diligence and tenacity. And when it comes to problem solving, you'll realize a bunch of things. One is if you try to solve a problem for several hours and you didn't get the solution, that's not a failure mode, because you succeeded in thinking and finding out a whole bunch of things that didn't work. That's a gain, not a loss. Because next time you solve a similar problem, you're not going to go down these dead ends so readily and waste so much time there. You'll bounce back and be much more effective. So trying and not succeeding is not a failure. Okay? And you need to understand that. Some people just think you don't get the right answer, they haven't accomplished anything. That's absolutely wrong. And in this class, you'll get a much more visceral grasp of this philosophy. And I will help you get there. That's one of the jobs I'm going to do for you. The exams, I'm willing to make them in class or take home. You can vote, and let's take a quick vote right now. How many want a take-home exam over an in-class exam? Take-home exam. Okay. How many want in-class exam? Oh, it's almost unanimous. It's amazing. But that's okay. So we'll take that. We'll take that vote again right before the exam to make sure you still feel the same way. Usually that vote pretty much stays the way it's happening right now. The exam schedule will be flexible. I'll give you a bunch of days where you can just do the exam for 6 hours anytime you want during that big time window, so you can schedule it around your other responsibilities and midterms or finals or whatever. No extra work for me, but it's hopefully better for you. So I want to basically help you at every turn, whatever, in every way possible. I'm going to treat you like adults. I'm going to assume you're responsible. And basically, I'm going to treat you the way I hoped that my teachers would treat me when I was a student, in your place, trying to learn stuff, many decades ago. So I teach the way I hoped I would have been taught back then, but of course, no such luck. But I try to do things a little bit differently and help you at every turn. I don't play gotcha with you. I don't try to make you stumble. I don't feel like I have to give a bunch of F's and D's and C's. If everybody aces everything, everybody gets an A+. I don't get an extra free toaster at the end of the semester from the dean if I give a few C's and D's and F's. Don't tell that to the dean. He may not like that. But everybody can win and win big. So it's up to you to do your part. And to help you do that, I'm willing to allow you to work in groups, say of maximum size 6 or so, study groups. You can work on the problem sets, and there'll be lots of problem sets. In fact, I already posted to the website. How many have actually looked at the website so far? Good. I'm proud of you. That shows initiative, right? Before the first lecture, you already looked at the website. That's great. The problem set's already posted. There'll be hundreds of problems, and none of them are due. They're not due on a weekly basis. I'm not going to grade you every day, make you turn in things on a Monday or Tuesday, and then grade it late if it's a day late. That's nonsense. You're not children. You can solve them on your own. You can work in groups. You know when you're right or wrong because your group members will tell you. You can even look stuff up if you'd like. But on the exam, you work on your own, and you can't look stuff up on the web during the exam. This class is not a class in Google searching. It's a class in problem solving, right? And you can do all the Google searching you want, but on the exam, you've got to work on your own. But I can assure you that most of the exam questions will come straight out of these problem sets, verbatim. And by most, I mean 5 out of 6, 6 out of 7 problems on an exam will come straight out of these problem sets that are posted on the web right now. So if you look at these problem sets, you already know what the midterm and final will look like. So what's the best strategy? Solve lots and lots of problems. And you can work in groups, and you can look things up, and you have the whole semester to do it. Now, I wish my teachers did that for me. I'm willing to do that for you. Now, why am I restricting group size to 6 people? It's kind of a technicality. Past semester I just said you can work in groups. I didn't put a restriction on group size. So one enterprising student said, okay, I'm going to form a group size of size 100 students. Each one will solve one problem. We'll all share the solutions without much work. Well, that's called crowdsourcing. And that student, I appreciated the novelty of that solution based on the fact that I forgot to specify an upper limit on the group size. That student should probably go to law school and make a heck of a good lawyer. But no, that's not what I want you to do. That's not the intent. That's terrible. That's not learning. That's just making an end run, around the knowledge without really assimilating it. And that's not why we're here. So don't do that. Don't try to. I don't play gotcha with you. So please don't play gotcha with me. That's a case of a student playing gotcha with a professor. It's not cool. It's not. It doesn't serve anybody. All right. So lots of exam questions on the problem sets. You know what to do. Solve as many as possible. Start today. Don't even wait till tomorrow. There's also extra credit readings and regular readings. So I'm going to also have on the website, already have on the website, in fact, papers and videos and certain books that I want you to read. And you can even pick and choose from those. There's many more than I actually expect you to do. And it's all on the website. So as a rough guideline, the midterm and the final, roughly a third of the grade. The readings is about 20%. Attendance is 10%. So you get 10% just for showing up. That's a good deal, right? And extra credit could be worth an extra 10% on top of everything else, so you can actually earn, much more than 100% here. And extra credit's kind of unbounded, actually. You can do as much of it as you like, and you'll just be better off. Any questions so far? So I'm giving you a lot of freedom here. And I hope that you won't abuse it, and I hope that you won't get lost in it either. Again, I'm teaching you the way I would prefer to be taught when I was a student. The professor doesn't play gotcha with you, gives you a lot of freedom, flexibility, doesn't dock you for being late here and there on some turn-in assignment, or doesn't make you turn in something every week like you were kindergarten children and that kind of thing. So I'm highly accessible. You can always send me email. You can, even catch me after class. I have office hours after class, after every class meeting. And of course, we have some great TAs. The lead TA is Nathan. Where is Nathan? Is Nathan here? Yeah, there he is, right there by the door. He's our lead TA, very smart guy. He's a PhD student in this area of algorithms and theory and all that good stuff. So he really knows his stuff. He's always happy to help. He's going to post the TA, and we have a few other TAs that are being hired right now, and their schedule will be posted on the website in a big calendar. You can see that they'll have a staggered set of hours across the week, across different days, across different hours of different days. So it's not always the same hour and the same day. In case you have a class, it won't clash because you can always find them at other hours on other days, and sometimes even on weekends. So you'll have a lot of assistance, a lot of help, a lot of TA backup that you can go to and learn stuff and ask questions. And also we're going to have even something better and more fun than regular office hours, and that's a Monday night problem-solving session. Usually it's Monday night, but we can see if people want to have it on a different night, that's okay too. But typically a Monday evening is a good time. And the TA will be there, the other TAs will be there, and we'll just go over problems. You come in, you ask questions, you ask them to solve certain problems, or give you help in solving certain problems, and it'll be like an interactive little section every Monday night. And not only that, we'll order pizza delivered. There'll be a bunch of large pizza pies every single time. My gift to you. So we'll make an announcement exactly what room and what time and what day that session is, but it'll be every single week. So please take advantage of that, if nothing else. A couple of slices of pizza. It's hard to go wrong with that. So here are some of the readings that I have in mind for you. The idea is to be exposed to a lot of cool stuff. The more you know, the more ideas, concepts, abstractions you're aware of and you can manipulate and connect to one another, the better off you are as a problem solver, as an effective engineer, as a scientist, as a thinker, and even as a good conversationalist at a cocktail party. When you know stuff, knowledge is power. They don't say that for nothing. So I want you to go through about 36 items over this course of the entire semester. So you have the whole semester to do this. About 15 videos at least, 15 papers, they're on the website, and about 6 books. And you can pick which ones you want. There's a whole bunch there. And of course, if you do more than that, it's extra credit. And you don't have to read a book cover to cover every single word, obviously. You can read some chapters, pick and choose. And when you submit your write-ups about that, basically write, say on a video, write a paragraph or two what you learned from that video. And all these are TED Talks, really clever TED Talks by impressive individuals, like the founders of Google and Bill Gates and Elon Musk and many other individuals that have changed the world and are still changing the world. Everything we do now, Steve Jobs and many others. This fascinating stuff. How many have seen TED Talks before? Good. So you'll get an opportunity to see many more, and for fun and credit. So it'll be very nice. And then a bunch of papers. These are short papers, 6 pages, 8 pages, lots of pictures. It's not even all text. So typically Scientific American articles about technologies, about theory, about math, about proofs, about the interactions of all these things with each other. Very cool stuff. You'll learn a lot of interesting ideas, concepts, abstractions, proofs, solutions, techniques, all sorts of it. Very, very worthwhile. So I'm sort of putting my money where my mouth is when I say it's good for you to watch TED Talks. I'm giving you credit in this course to watch more TED Talks. I'm not just saying do it because it'll help you, which of course it will, but do it for a grade now, on top of it being good for you anyway. So on the website, some talks and papers are highlighted in red font. Those are the required ones. So a few I actually want you to read specifically or watch specifically. The others are kind of optional, pick and choose. How many have seen the last lecture by Randy Pausch? Okay, so he was a friend of mine, my mentor actually, when I first joined UVA. And then he gave another great talk at my request called Time Management. This is Cabell Hall, standing room only. How many have seen the time management talk by him? So I organized the whole thing actually. The backstory is pancreatic cancer, late stage pancreatic cancer. He only had a few months to live. His wife didn't want him to go anywhere, just be with the kids and with her. And I got him to still give this time management lecture in the last few months of his life. And the way I did that is, he was a big Sting fan, the singer, the Police, the band. And Sting was giving a concert here at UVA. This is back in 2008. And I got Sting to meet his wife backstage. And that's how we got her to agree that Randy would give this lecture. So it was pretty sly, and don't ask me how I managed to do that. It took a lot of doing, actually. But I'm a problem solver, so not a problem I pride myself of having solved. Otherwise, this lecture wouldn't exist, and you couldn't watch it. Now, I'm asking you to watch it very deliberately. Powers of 10 shows you the scale of the universe. Very important. Keeping an eye on the big picture, that's what it's about. And let me show you an example of the big picture. So this is another application. This is focusing in. This is the scale in meters and showing you relative sizes. How many have seen this before? A few of you. Okay, it's very cool. And you can click on each and every one of those and stop and go and learn a bunch of stuff. So here's an ant, and that's a few millimeters across. right? Mites, grains of sand. This is the thickness of paper right here, right? And here's yet smaller stuff. Skin cells, drops of mist. Here's wavelengths of light. Here's a chromosome, right? Bacteria and viruses. We're now at a millionth of a meter, thousandth of a millimeter. Transistor on a chip. It's much smaller than bacteria, it turns out. That's why there's so many billions of them on a single chip, right? DNA. That's about the width of DNA. Here's a scale again, 10 to the minus 9 roughly, a millionth of a millimeter. And then, of course, you have atoms already. This is an angstrom. Here's a hydrogen atom. Right? Here's really short wavelength, like gamma rays. And notice here now there's empty space a lot, because there's not a whole lot happening in the atom once you get past the electron shell until you get to the nucleus. And then within that, there's even smaller things like quarks and other even smaller subparticles. And we don't even know if lengths less than this Planck length are actually meaningful to even discuss. The universe may be quantized. The universe may be digital. It's like Neo in the Matrix kind of stuff. The universe may be pixelized at a very, very small level. And now, most of the theories about that, people are investigating it. And then there's quarks here at the very, very bottom level. So we're zooming in, about 10 to the 25 powers of 10, from everyday life. And here we are zooming back out. This time it's more quick because you've already seen this part. And then we're going to keep zooming out. So here's a mouse, here's a basketball, here's a human being, 6 feet roughly. Some crabs actually are bigger than humans. Here's elephants, T-Rex, right? Some trees are quite large, right? Bigger than jumbo jets. Here's Statue of Liberty, Titanic, Eiffel Tower, Hoover Dam. So these are bigger and bigger objects, and now you're into 1 kilometer, roughly, in terms of scale. That's about a mile, 2/3 of a mile. And there's Mount Fuji and other things, Rhode Island. The entire state of West Virginia. Here's California, which is big. Now certain moons and planets will kick in to the picture. Right? There's our moon. There's many other moons. Here's the entire Earth now, at 10 to the 7. Here's the world of Minecraft. It's bigger than Neptune. Who would have thought? That's amazing. How many play Minecraft? It's pretty cool. The entire sun is right there, our sun. But look at all these other suns, other stars. Here's our sun again, right here, this little yellow dot. Look how much bigger these other stars are than our sun. You can't even see the sun right now, but look at these stars. They're literally millions of times bigger. If one of those stars was where our sun is, we'd all be in it right now, inside it. The whole Earth would be inside that star. Of course, it wouldn't be. It would just be plasma. But some nebula. Now we're into 10 to the 15 meters. Right? Here's an entire light year. This whole distance is light year. Light will take a year to travel this distance here. That's how big the scale is now. A parsec is roughly 4.5 light years. Right? The Millennium Falcon can go through 12 of those. Never mind. So it's pretty cool. So this is about the big picture, keeping in mind powers of 10, the effect of exponentiating. In computer science, there's a lot of exponentiation going around, usually powers of 2, but it's equivalent with powers of 10. And just a beautiful way to think about the universe, just hierarchies and hierarchies of containments of objects and structures and so on. It's just pretty amazing. Here's the whole Milky Way. That's 100,000 light years across right here. 10 to the 21 meters. That's the entire distance the Earth has traveled through the cosmos since the time it was created. And then, of course, some of these bigger structures are still being investigated and discovered, and we don't even know completely what's out there all the way out, except for how far we can see, which is a few gigaparsecs, about 14 billion light years out, the entire observable universe. Anyway, so again, the reason I'm showing this to you, there's many reasons. One, if you've never seen this before, it's very cool. And if you look at the app on the web, first of all, you get extra credit if you go through this on the web. Click on a bunch of things. You can learn about each and every one of those objects and You can follow links and so on. That's pretty cool. But keeping in mind the bigger picture is always very, very useful. Don't just get into a habit of being myopic, only caring about one little sliver of what you're presented and not looking left or right. That's not good science. It's not good problem solving. It's not very interesting to go through life like that. Always kind of look broadly at things, and you'll be better off for it. Whether you're a thinker, a creator, an artist, a Google engineer, whatever it is you do. So another good video I want you to see is Claude Shannon, the father of information age. He's really the father of information theory. He invented digital circuits just for his master's degree back in the 40s at MIT. Very, very high impact this guy had. And another good TED Talk is about the pattern behind self-deception. Michael Shermer, he published the Skeptic magazine. So always keep a skeptical mind. And by that I don't mean don't believe anything. I mean question stuff in a reasoned way, in a rational way, in an intelligent way. Don't just accept things at face value just because somebody in authority told you that that's true. You know, that most of the world problems boil down to exactly this phenomenon. Somebody tells something, the following is true, and they just believe it as is, no questions asked. Many wars, many holocausts have started that way. Think about it. All right, other required articles. There's an ancient computer that dates back over 2,000 years. And the Greeks actually built it. And we discovered it in its fossilized form, and we investigated it. Very, very interesting thing. But the Greeks have built a computer 2000 BC. It was a mechanical computer. Electricity wasn't discovered yet. So it was cranks and levers and gears and so on. But how many knew that? The Greeks had a mechanical computer. It's amazing, right? If they followed up on that, and other empires that followed the Greeks, the Romans and others, that followed up on it and kept developing that, we could have had iPhones 1,000 years ago. And we could have been populating the various moons of the solar system by now, except we weren't so lucky. There were all sorts of other things going on, like holy wars and crusades and the Dark Ages and inquisitions and all sorts of nastiness, which really held back all of civilization. But we're still doing pretty good. At least we have iPhones today. We could have not had them for another 1,000 years. That would have been even sadder. But it's good to keep this in mind. It's good to read about these things. Of course, Alan Turing, the big hitter in computer science, there's a lot of articles about him, and even the ideas that, like, people forgotten that he's done are also very, very amazing. Not just the ones that we all know about, that he helped save, us from the Nazis during World War II by breaking the Enigma code, right? How many have seen The Imitation Game, right? That whole movie was about that. Pretty amazing. And of course, Richard Hamming, there's an article about you and your research. Scott Aronson, who can name the bigger number? So these I want you to read, and the rest you can pick and choose as optional. And there's The Imitation Game, and if you want to, watch the movie again, or just send me a couple of paragraphs, maybe a page or so about what you learned and what was cool, what was interesting, I'm going to give you extra credit for watching movies. And it's, how cool is that? I wish my teachers did that for me. I had to watch movies for free. Well, I had to pay to watch movies. You get credit for watching movies. And there's a handout on the website about basic concepts. That's one of the required readings. Just go through it. It's only about 10 or 12 pages, but it'll tell you what numbers are, what sets are, what intersection and union and complementation of sets and De Morgan's law and a whole bunch of basic discrete math concepts that if you're not sure about or are rusty about, brush up on it. And this is sort of the go-to document to do it. About 10 or 12 pages of definitions, basically, and examples. Very good to go through. So don't take things for granted. This is one of my favorite cartoons. Kepler trying to explain to his colleagues. So you see, the orbit of a planet is elliptical, but he's taking a lot of things for granted because his colleagues have no idea what's an orbit, what's a planet, what's elliptical. So you have to kind of really explain things from scratch, from first principles, and that's what we try to do in this course, to explain everything from first principles. So this is kind of a snapshot of this document. Also, actually, this is a different document showing you other things, including reductions, one-to-one correspondences, sets, infinite and finite, dovetailing, diagonalization, all sorts of other stuff. So again, that's on the class website, as a kind of condensed summary of these concepts you can go to and always look things up if you need to. You won't have to look far. So we mentioned Polya, how to solve it earlier. I want you to read that for sure. Infinity in the Mind by Rucker. He'll talk to you about infinities, different kinds of infinities, different sizes of magnitudes of infinite sets and how they relate to each other, how they can be mapped to one another using one-to-one correspondences, what are bigger and smaller infinities. We used to think as a species there's only one kind of infinity, and it's very big. Nobody up till late 1800s thought much about infinities except Georg Cantor did, and he really developed a whole theory of infinite sets and infinite transfinite arithmetic. It was pretty amazing. A lot of stuff depends on that, and including in this course. So it's very, very good to know about infinities. Thus, you can always amaze and boggle your friends with questions about infinities that they'll be very surprised by, and we'll see some examples of that pretty soon. Carl Sagan in The Demon Haunted World, it's a lot like the Skeptic magazine except on steroids, and he also teaches there how to not fall into false beliefs and beliefs without evidence, and how to question things in a reasoned, polite, but persistent way, and not just take things because somebody told you to. In problem solving, it's very important. It's also very important the rest of life. Right? A lot of society's ills come from people believing things that are simply not true or don't hold up to scrutiny. We've seen a lot of that in the last few years. And this is a fun book, What If? Randall Munroe. So he does the XKCD cartoons. How many have seen those? They're pretty cool, kind of pencil kind of figure cartoons. And here he answers a bunch of hypothetical questions in a very scientific and reasoned manner, and it's pretty funny in a geeky kind of way. So I think you'll enjoy it. So look at that as well. Okay, and then the rest are sort of electives. There's a whole bunch of stuff. Submit about 2 or more per week. So that I want you to do 2 of those per week, whether it's articles, TED Talks, these write-ups, videos, whatever. Some of them are graphics, animation, demos, whatever it is. And I don't want to create extra hurdle for you, but I want you to avoid cramming. Some people, when I didn't say 2 a week, some people just waited to the very end of the semester and then try to watch 50 TED Talks in one weekend. And that's just stupid. That's not watching TED Talks. That's just going through some strange, bizarre exercise of, I don't know what they're thinking, but you're not really learning anything if you just watch TED Talks for 30 hours straight. It's kind of silly. So don't do that, please. Just do at least 2 per week, and you should be fine. It's not very onerous. They're only 15, 20 minutes each at the most. Some of them are just 10 minutes. And just submit for an article, 1 to 2 paragraphs for an article or a video. For a book, the book is bigger, so maybe submit a page or 2. What you learned in the book, what was interesting, what was surprising. Again, not to make extra work for you, just to help you focus on the important things and kind of summarize it for yourself, even more than me. And submit everything to this class website. This is a universal submission class website or email address, I guess, in Gmail on Google. Everything goes to there, and the TAs will all pick it up from there and keep track of it. So 36 total, but do more for extra credit. It's always good. So I'm giving you a lot of options. Here's some, again, snapshot of a few papers that I have stuck on there. We'll just breeze through this. You can look it up on the web more specifically. But things about quantum computing, biological computer, the history of computing, security and privacy, kind of the future of computing. So this is like projections into the future, where computer might be going, in 5 or 10 or 20 or 30 or 100 years even. Kind of web-type science, and of course Wikipedia is a great resource. Always fall back on that if you have to. Wikipedia has wiki pages on all the subjects in this course, including Chomsky hierarchy and computational complexity and data structures and everything else, from the languages. It's a very, very good resource. Knowledge and distillation of information in a nice, consistent way. And there's other things. So ask questions right away. Don't let questions kind of fester, because in this course, things will build very heavily on previous things. It's very kind of incremental knowledge that builds on previous knowledge. So if you don't understand something, if you just wait arbitrarily, it may compound, and then you won't understand things that then depend on that, and it could spiral out of control. So ask questions very quickly all the way to the beginning, and I'm always happy to answer questions. There's no such thing as a silly question. All questions are important and good, and if you ask a question, realize that by asking it, you're probably helping the 1/3 of the rest of the class here, because they probably have the same question, but are too reluctant to ask. So if you ask it yourself, you'll be doing them a favor too. So you're helping your peers actually by asking questions. Of course, attend every lecture, attendance is 10% of the grade, and occasionally we're going to use a probabilistic algorithm to take attendance. What that means is once every couple or 2 or 3 lectures, I'm going to pass an attendance sheet that you'll have to sign, not necessarily every time. So today we're not taking attendance, but in a lecture or 2 we may take attendance, and you won't know which because we're going to flip a coin every time, so we don't really know when. And that's to keep everybody on their toes. So again, not to create more work for the TAs or for me or for you, but showing up is important because we're going to talk about a lot of stuff in lecture that is not even in the book, obviously, right? Because the book doesn't have TED Talks, and the book doesn't have these cool animations, one of which we just showed you, and all sorts of stuff. So a lot of stuff will happen in class that you can't really go to the book to. Of course, the class website will have all these slides, but even then, explanations that we have here, Q&A, clarifications, enhancements of what we're discussing in terms of follow-up discussions, all that will happen here too, and that's not in the slides, it's just stuff that happens because of the slides. So it's very important to be here. The most important thing is solve lots of problems. There's only one way to become a better problem solver, is by solving lots of problems. I know it sounds obvious, but a lot of people don't do that. A lot of people go to a Google interview and they know they'll ask you all sorts of clever questions. How have you been to a Microsoft or Google or Facebook or Twitter interview and they ask you all sorts of quirky, clever questions during the interview? I don't know how many of you interviewed a lot yet, but they ask you all sorts of kind of MacGyverish kind of questions, and if you just sit there and stare at them, you can forget about the 6-figure salary. You may have to, write device drivers for Microsoft for the rest of your life for only 5 figures. Not that it's a terrible existence, it's just not as cool as doing the other stuff. So it'll prepare you to just be more impressive at interviews and problem solving and working for these high-tech companies and inventing the future, along with your colleagues at these companies for decades to come. So it's hard to overestimate how important solving problems and becoming a better problem solving is, and that's one of the things we'll focus a lot in this course. So when you say problem solving, we used to kind of go to MacGyver as the quintessential, problem solver, creative thinker, out of the box kind of, solution guy. Of course, now we can do even better. We got Matt Damon. How many have seen this movie, The Martian? It's like the epitome of amazing resourcefulness and problem solving. He basically survives on Mars for 2 years on a potato. Not quite that bad, but it's pretty amazing. So extra credit, watch this movie if you haven't yet. It's a mindset, of resourcefulness, how to do more with less. And when you talk about algorithms and math and proofs, it's exactly the same mindset. It's no different than Matt Damon on Mars. Of course, he had a lot more writing on it than, a grade in the class, right? Okay, so speaking of problem solving, let's solve this problem that we showed you an hour ago. Can you spin up 5 test tubes in a 12-hole centrifuge? So let's take another poll before we even start. How many say it's possible, 5 test tubes simultaneous? How many say probably not? There's still people voting either way. That's okay. That's fair enough. Any thoughts, ideas? Let's do it interactively. What the heck? We're a large group, but there's no limit to interactions. Yeah. All right. Can somebody paraphrase or explain why his solution will work or not work, or have another solution? I assume not everybody in the class heard what he said. But. Yeah, he says when you tighten a tire on a car, like you're replacing a flat tire, you tighten alternatively different bolts, not one all the way down, because then it will kind of skew the tire on the wheel, or skew the wheel on the brake assembly, or whatever it is. Any other thoughts, ideas about this? So can you spin 5 test tubes in a balanced way in a 12-hole centrifuge? So what's some of the questions you should be asking me, or yourself even? Yeah. Yeah. So I asked you, is there a way to do it in a balanced way? And I never said what is balanced. So very good. So she's saying, what's the meaning of balance? So you tell me, what does a balanced rotation mean in a centrifuge? Okay, so let's hold off on the solution. Let's first answer this question. What does balanced mean with respect to somebody or something rotating? Equal angle distance between each. So he's saying if it's like equally spaced around the circle, it'll be balanced. How many agree? If it's equally spaced around the circle, it'll be balanced. How many say it's not the complete definition, but if it is equally spaced around the circle, it will be balanced, but that's not the only things that will be balanced. Good, now we're getting something. So he's right, but there's other things that may not necessarily be equally spaced. So what's the complete general definition? Yeah. Okay, she's saying all the forces are equal and they cancel out. So if every test tube is like a vector pointing to the test tube, essentially what she's saying is the sum of the vectors will be equal to 0. That'll cancel out. So now we have to find 5 vectors that will add up to 0. And these vectors can only point to these positions, the hours of the clock. They can't point to arbitrary directions. They can't point to a non-hole. They have to point to these places where the test tubes can reside. Or we have to prove that no such collection of 5 vectors exists that add up to 0. And that's a tall order. Plus, when you start talking about these vectors, you're going to talk about sines and cosines of 30 degrees and 90 degrees and 60 degrees or whatever the angles are, something 15 degrees. You're going to talk about irrational numbers and sines and cosines. And now we're going to go down this rabbit hole that we'd rather not go to unless it's absolutely necessary. And it's rarely necessary to go down rabbit holes which are too big and too obscure, as you'll see again and again in this course. There's often ways to reason about things are much simpler, more elegant. Occam's razor, less is more. So let's get away from vectors because it's going to be a mess. Yeah. Okay, so what does spinning mean? What does balance mean? So somebody come up with a more general definition other than vectors. Sure, if you have a bunch of vectors not up to 0, okay, maybe it's balanced. But come up with a simpler way of saying it or looking at it. Don't mention vectors even. Yeah. The average position. What does the average position mean? He's on the right track. In fact, you're correct. Is there another word for that up there? Yeah. The center of mass. Is that what you were going to say up there? Yeah. So the average position is basically the center of mass. It's a weighted average of all the particles in the system, whether it's a centrifuge or a solar system or anything in between. So if the center of mass coincides with the center of rotation, it's balanced. If the two are off kilter one another, it's not balanced. How many believe that? Yeah, that's a complete characterization. Now, if everything was equally spaced, like was said originally, the center of mass will coincide with the center of rotation, no problem. But that's not the only time that would happen. There's other times where that can happen too. What do you say? Okay, so he's saying start adding or subtracting fluids from the test tubes, but they're all identical. Remember, you can't mess with the test tubes. Although, if you could, that would be a solution. You could start adding and subtracting test tubes into one another, and maybe you can get it to balance that way. But you're stuck with the equal, identical test tubes with equal size, equal mass, equal amount of fluid, equal everything. All the test tubes are indistinguishable. You cannot modify them up there. If it's balanced when it's standing still, it'll be balanced when it's rotating. If the center of mass coincides with the center of rotation, it'll be balanced no matter what the configuration is. So let's keep going. So we already had a solution way up in the beginning of the discussion, and it was correct. Anybody want to regurgitate that or come up with a solution or explanation? So you can spin up 2 test tubes like this if you want. Right? And what else? Keep going. Yeah, so you can spin up 3 test tubes like this. They're equally spaced. So the blue ones are equally spaced, but these are 2 separate configurations, 2 separate centrifuges. What's the key insight here, do you think? We're almost there. Maybe somebody who hasn't spoken yet today speak up. I want to get more people participating. It's fun. You'll see, you'll feel the rush, the adrenaline going when you speak up because, it takes courage. So, yeah. Yeah, so he's saying the center of mass of the 2 red ones is in the center, obviously because it's balanced. The center of mass of the 3 blue ones is in the center. So if you put them on top of each other, if you superpose them, it'll also be balanced. He's saying basically that these 2 vectors add up to 0. These 3 vectors add up to 0 also. So if these 3 vectors add up to 0, these 2 vectors add up to 0, all 5 vectors add up to what? Also 0. Because addition is associative. Right? Now we have an interesting basic principle. Addition is associative, so it doesn't matter what order you add up the vectors. So basically you can merge these 2 solutions. So get ready for it, Here we go. We're merging these 2 solutions. See it again in instant replay? There we go. And this will be balanced too, because of the associativity of vector addition, or any addition for that matter. And it looks kind of funky. Look at this. It doesn't look symmetric. It's not equally spaced. There's 2 here, only 1 there, and it's kind of funky looking. If you rotate it a third of the way, it won't look the same as you started. But it will be balanced. How many believe that? So now we're getting somewhere, but we're not going to stop. So now we have an answer. The answer is yes to the question, but we're not going to stop, which is another interesting problem-solving principle. When you get to the right answer, keep going. You'll have more insights, more generalizations, more observations about what went on, deeper understanding of the principles. Try to generalize things. So let's do that. So this is a principle of superposition, and this is more powerful than just 2 plus 3 is 5. Any number plus any other number, their sum must be balanced, right? So if so now you know that 7 can be balanced. How many believe 7 can be balanced? Why? Short reason. 7 is 2, 2, and 3, or it's 5 and 2, because we already know 5 is balanced. Add 2 more. So does that mean that any sum can be balanced? What about 9? It's 7 plus 2. What about 11? It's 9 plus 2. 2 is balanced, 9 is balanced. So does that mean 11 is balanced? Because 11 is 9 plus 2, and you can superpose a 9 on a 2? How many say 11 will balance? Oh, good. You're right to be skeptical. Why won't it balance? Yeah. There's one missing hole. What's wrong with the missing hole? Why? Yeah, you're right. How many see that if you have 11, it's equivalent to having 1? You can think about spinning 11 masses, or you can think about having a solid centrifuge with all the holes plugged up, and you're spinning 1 negative mass. That's a hole. How many see that those 2 scenarios are equivalent from a physics point of view? Holes are negative masses. But what's the real principle here at play? Extract a general principle from this. If you can spin K test tubes on 12 holes, what other number is guaranteed to be spinnable also in a balanced way? Generalize it. So K is possible. What else is possible? 12 minus K. How many get that? If you can spin 5, you can spin 7. Why? Because you can finish it, right? You can take these 5 out and fill in this 7 in. And it amounts to the same thing. because 12 is the 5 plus 7 and 12 spins balanced way. Right? So again, take out these 5, put in these 7 where the holes were, and that's guaranteed to be spinnable also. What would you call this principle? Complementarity. You're complementing the configuration, and that's guaranteed to be another solution that must also work. How many get that? So now we expose another basic principle here by not stopping when we had the answer, but kept going. There's a principle of complementarity. So if K can be spun in a balanced way, the number of holes minus K could be spun in a balanced way, and in fact that solution would just be negating the original solution. Take the original test tube out and put test tube where the holes were, and that's guaranteed to work also. And the reason that even two solutions can be superposed is a principle of superposition, but it works because superposing solutions are linear, and a linear superposition of solutions is also a solution. So when you have a linear system, two solutions to a linear system, whatever that linear system is, added up, two solutions to a linear system added up must also be a solution to the same linear system. And a linear system doesn't have to be centrifuges. Give me other examples of linear systems. It's a very powerful principle in a linear system that the sum of solutions is also a solution. What other examples of linear systems can you think of? In nature, the universe, in real life. I'll give you a hint. Physics is full of them. Ordinary differential equations, linear equations, linear algebra, it's linear systems. Forces, like gravity. If you have two bodies, their effect on you is the sum of the two forces added up on you as vectors. How many get that? That's why we have orbits in the universe. That's why the Earth rotates around the sun. Because of this principle of linearity and superposition of vectors and forces, and the fact that the sum of two solutions to a linear system is yet another solution to that same system. Whether it's a gravitational system, a centrifuge, a bunch of linear equations, differential equations too. Very, very powerful principle. Now we can see all of a sudden the light is shining on your mind. This is a lot of insights that you wouldn't get if you stopped right there with yes on 5 test tubes can spin and walked away in victory as if you just won the lottery. No, you didn't. You just happened to get the right answer. That doesn't count for much anymore, not from this point forward. Getting the right answer. It's nice, don't get me wrong, it's better to get the right answer than a wrong answer, but that's just the beginning of the big trail of wins that you'll garner if you keep going after that. And we're not done yet, right? You can also look at empirical testing. So I actually once showed this problem to a colleague of mine who's a biologist. He works with test tubes and centrifuges in his lab every day. And he said, no, you can't spin up 5. It's got to be 3. It's got to be equally spaced around, like was discussed earlier. Sure, those solutions work. And he didn't believe that 5 works. I showed him this set of reasoning here about complementarity and linearity and superposition. And he said, no, I see it. I see what you're trying to get at, but it still won't work. It doesn't look right. It looks all off kilter. And I said, what would it take to convince you? And he said, let's test it empirically. I have centrifuges in the next room in his lab. So we walk over to the centrifuges. I go, okay, curious to see where this is going to go, right? This is one of those, defining life moments, at least for me. I don't know if it was for him, but so we walk into the centrifuge. He gets his postdoc. He says, fill up 5 test tubes. Be very careful to make them equal amounts of, distilled water and so on. And, put them like this, but start very, very carefully because we don't want to damage the centrifuge. If you spin it up and it doesn't, remain balanced, it'll start, doing like what a washer or a dryer will do when you put one sneaker and it goes into a spin cycle and start vibrating in the washing machine. It'll start marching across your room, make a lot of noise and be kind of silly looking. But with a centrifuge, something worse would happen. The thing spins at 60,000 RPM. That's 1,000 revolutions per second. And if that thing goes off balance and flies off its hinge, it'll go through the nearest wall and keep going. There's so much kinetic energy in that it can kill somebody. So he said, be very, very careful. So the postdoc starts to spin it, and it goes up and up in the RPM, and perfectly still, no vibration. It keeps going up, and the guy seemed kind of surprised. Like, listen, well, crank it up, full force. No vibration, perfectly still. Turns to me and says, now I believe you. This is the classical kind of friction between theorists and pragmatists. On a good day, the two shall meet, but on other days of the week, they kind of talk past each other sometimes. They don't have to. You can have both. You can have good theory and good practice and good empirical testing and so on. It's all good. So anyway, this thing actually happened. I'm not making this up. I probably couldn't make it up if I tried. It's a pretty good story. So always do some empirical testing if you can. If you come up with algorithms, you analyze data, you think something should sort or sort quickly or whatever it is you're doing, test it. Test it a lot. Test it on different things and make sure that it behaves the way you expect it to behave. And then that corroborates your theory. The theory was still correct to begin with, but now you have empirical evidence that back it up. And guess what? Occasionally a theory is not quite right. And when you start to test it empirically, you'll see the differences. You'll see the discrepancies between the theory and the practice and the experiments. And then you have to go back and scratch your head and think what's wrong with the theory, or maybe what's wrong with the experiments. Maybe the theory is right, the experiments are off kilter. But you'll find out something new either way. Either the experiments were designed badly or not measured correctly, or the theory may be wrong, and then you have to go back and fix the theory. And this happened many times to the human species throughout our evolution. Right? Einstein did this. Turns out that Newton's theory was pretty good, but not quite correct when things were moving fast or masses were very large and things like that. And Einstein fixed that. And others are trying to fix Einstein's theory with respect to quantum mechanics and quantum gravity and other very esoteric things where relativity begins to fail around black holes in the vicinity of event horizons and so on. So we need yet more theories that are even correct for Einstein. And believe me, it's hard to correct Einstein. He got a lot of things really, really right. There's hundreds and hundreds of experiments that all corroborated exactly what he said, how he said it, how the universe works. But still, no theory is complete. After all, we invented all these mathematics and symbols and relationships and functions and so on. The universe, we did not invent it. It was here a long time before us, and it will be here a long time after we're gone. And so there's bound to be some discrepancies between our little symbol pushing on a piece of paper and how this grand place works around us, and we find ourselves in this magnificent grand universe. So that's part of our job as a species, to figure out what's going on, and we're making good headway towards that. In fits and starts, but still a lot of progress. Notice, no vector calculus was used. We didn't use trig at all in this slide. You can explain this to somebody in a cocktail party who's an architect or an artist or an English major, and they'll get it fine. Because you expose the basic principles at work. That are much more powerful than adding vectors together made up of sines and cosines and square roots and fractions and so on. That's hard to understand. It's not very convincing. If you understand it, you just check that the math is right. You still don't understand why it's right. You just know that it is. That's not understanding. That's just regurgitating symbols and walking away as if you won some big prize. You didn't. Your understanding is obscure. You didn't get many insights. You didn't generalize things. There's no equations at all, not just sines and cosines. Truth is guaranteed. Once you understand this principle, this has no choice but to be true. That 3 and 2 are balanced. It's so simple, truth has no place to hide from you. You exposed it. It has no place to run. Can't get away from you anymore. You nailed it down real tight, very simply, very dramatically. And that's problem solving at its best. Occam's razor just permeated this whole discussion. Very, very important insights. You generalized things as you went, and that gave you a whole bunch of other solutions. Because if you use vectors, let's say you use 5 vectors, sines and cosines, they add up to 0, you walked away, whoopee-doo. But then I said, okay, can you spin 23 test tubes on a 360-hole centrifuge? You would have to start from scratch. That would be a much harder problem. But now you can answer the question I just asked you. Can you spin 23 on a 360-hole centrifuge? How many say yes? How many say no? How many say yes? Good, there's more hands. Why? Why is now that question is easy? 23 test tubes, 360 holes. It's a giant, big centrifuge. But yeah, it could work. Why? Yeah, and what would you superpose? Yeah, 2, 2, 2, 2, 2, 2, 2, 2, and finally 3 to get to the odd one. End of story. How many get this? Now you can solve an infinity of problems, all of which would look horrendously hard if you didn't expose the basic principles, which make you much more powerful now in terms of dominion over this problem and lots of other related problems. So when you get the right answer, for your sake, for the sake of understanding, for the sake of science, for the sake of progress, for the sake of deeper understanding, keep going. Don't stop. By the way, doing that, there's a name for that. It's called research, just so you know. Not stopping when you got the right answer, but keeping going and generalizing and applying it to other things and exposing principles and coming up with theories. Now you can generalize this stuff very, very easily. Before, with sines and cosines, you have no chance. And it's elegant. It's beautiful. It's aesthetic. How many get that? This kind of reasoning, this kind of solution, as opposed to quick and dirty sines, cosines, myopic solution that only works for one case and you can't do much with. So let's try it again with another problem. The sum of integers from 1 to 100. Legend has it that when Carl Friedrich Gauss, the great mathematician, was a 7-year-old kid in kindergarten back in the 1700s, the teacher tried to get the kids to be busy for an hour, so the teacher gave him the assignment to add up all the numbers from 1 to 100, figuring that's enough to keep a bunch of 7-year-olds busy. And you know, it worked on everybody but little Gauss, who was 7 years old, and he came back after 2 minutes saying that the answer is 5,050. And the teacher just couldn't believe it. And the question is, how did little Gauss do this addition very quickly? And he didn't use induction. How many heard of induction? Good. In this course, we will almost never use induction. My gift to you. And I'll explain why in a minute. All right, so he basically added up the numbers like that, then added them up backwards like this, and every column adds up to 101, right? Because 2 plus 99 is the same as 3 plus 98, and all the way to 101. And how many 101s do you have here? 100. So the total sum of all these green guys is what? 10,100. But now we got to divide that by 2 because we added everything twice. So we got to take half of our sum when the sum is 10,100, and so you got to take half of that, and it's 5,050. And you know, now you can see it. You know, it's pretty good. It works. Now you can add up numbers from 1 to 1,000 too, and this gives you a formula for the sum. That's even better. You know, so it's pretty impressive if you do this in a Google interview, you know, this quickly. But for a 7-year-old to do it in kindergarten, that's even better. That's why it was called the Prince of Mathematics, and he did many, many other things besides. But let's do it even better. The sum here is the area of this staircase, because here's 1 unit, here's 2 units of area, here's 3, here's 4, here's 5, 6, 7. So how many can see that the area in red is the sum if you take it 100 stairs up? The area is the sum. And you might wonder, well, how do you compute this area? And there's lots of ways to do it, but you know, we're not going to use induction because I just said induction should be avoided if possible. I'm not saying it doesn't have its uses. I'm saying it should be avoided if possible. Same thing is true about nuclear weapons. Occasionally, on very rare, extreme occasions, they have their uses, but in general, they should be avoided. And let's hope it stays that way going forward. But anyway, I digress. Take this staircase. Painted blue. Now you have 2 staircases. And flip it over and put it on top of the first staircase. And now it's no longer a staircase, it's a rectangle. Rectangles are easy to compute areas for, right? What's the area of this rectangle? Well, it's however many stairs there are, and on the other direction, it's that plus 1, because you have all the red stairs plus 1 blue one that gets flipped over. So what's the formula for the sum of all the integers from 1 to n? Right out of this picture. Somebody who hasn't spoken yet today, say something. It's a rush, adrenaline, you feel it. You get points for courage just for speaking up. Never mind what you say. Yeah. Yeah. N times n plus 1 over 2 because you're doing it twice and you just need to do it once. Now you got a formula. Now if you use induction, this formula has to be given to you and then you prove that this formula is true using induction. Induction doesn't give you the formula, it verifies the formula. It's one of the many drawbacks of induction. And I'm going to list for you next time a whole bunch of other drawbacks. But that's very insightful. Now, you may not remember induction in 20 years when you're sitting in some cocktail party, but you will remember this staircase. And you'll remember why it's true. And the staircase tells you why the formula must look like this. It's not an accident that there's a 2 in the denominator. Why is there a 3 or 4 or 7 in the denominator? Because there's 2 staircases, not 3 or 4 or 7. That's why there's a 2 there. Induction doesn't tell you that. This picture does. Why is it n times n plus 1? Why is it n squared times n plus 7? Well, because it's the area of a rectangle, so it's width times height. And one of them is n, and one is 1 larger than it. And that's why it's n times n plus 1. It's not n minus 2 times n plus 3. That won't make sense from this picture. So now this picture tells you exactly the formula of this formula. It's got to be quadratic. The denominator is going to be a constant. It's going to be 2 and not 3 or 7 or pi. And that's a lot more insight than you had before on the sum of integers. So we didn't just stop there. We kept going. And you can go other proofs and have more insights too. Right? And next time we'll pick up this discussion. All right. See you then.
I received an email from you prior to